Okay, we'll go from current slide. Not quite there yet, but we're close to it. Okay, first, any questions on anything we've done so far? Second, just a reminder, as we discussed last week, today, Thursday, and Tuesday, we're going to be going an extra half hour. Okay, we'll go from 4 to 6 rather than 4 to 5:30, so I can be out of town Thursday of next week. So I'm not going to be out the whole day, but so we can leave early because we've got a fairly long trip to make, and my wife nor I want it to be very, very late at night, early morning getting there. So we're going to be leaving a little early. Okay, so today we'll go till 6. Is that okay? And if not, we are recording. I was going to say, if not, you'll have to look at a previous recording like I did for last spring and try to follow along there. But we're in it now. I don't know if you've noticed this, if you've looked at the YouTube videos. The YouTube videos we do now are all at the bottom of the playlist. Okay? The ones at the top of the playlist are the ones I did last term when I first taught this course. And so every time when I record a new class, I go back and the class I did last time, then I take it off. I don't take them off ahead of time for such in a case as this, that the system goes down or something. That way there will always be something fairly close to what we're doing out there. So I thought I was going to have to use that today, but I don't. We're here. All right. Now, we talked last time about what an atom was. Remember? Smallest object, smallest particle, subparticle, smallest little bit of matter that will still be that element. Okay, that's an atom. That you can't subdivide it any further and still be that material. Okay? Iron, if you got it down to the atom, can't go any further than that. Okay? Now, for compounds like carbon dioxide or rust or ammonia or something like that, you can get down to a molecule. And that's as small as you can get and still be the material. But for an element, an atom is as small as you can go. Does that mean that's as small as you can possibly get? No, we know now that there are particles that make up atoms, but they're not going to be that material anymore. They're just going to be these particles. Okay? And these particles have 3 names. Now, these are the major ones. There are minor ones as well. The proton. Anyone know anything about a proton? Well, P, proton, positive charge. A proton is the only major particle within an atom that has a particle charge, a positive charge. Okay? It's fairly massive for the material, still awfully small, but much bigger, almost 4 times bigger, more massive than an electron is. Okay? Now, it has a fixed diameter. It's awfully small, but it has a positive charge. Now, the electron comes next, and there's nothing I can give you a mnemonic device to help you remember this, but it's almost massless. I mean, this is such a tiny mass, about 1/10,000th that of a proton. Not quite, a little bit more than that, between a thousandth and a 10,000th. So it's really, really small. No measurable diameter at all. We can't measure anything nearly that small. But it has a full negative charge. So this fairly massive thing, proton, has 1 positive charge. This almost massless electron has 1 negative charge. And then there we have the neutrons. And here's the key on that. Neutron, neutral. Okay, you can almost see it there. Neutral. No charge at all. Okay? I'm not talking about what you pay for the course. Okay? No. All right. Is it Kayla? Okay. Okay. All right, we're talking about what makes up an atom. Protons, positive charge, electrons, negative charge, neutrons, no charge. The protons and neutrons, and by the way, they say the zero size here is due to lack of any internal structure. There's not much there that makes up an electron. There's plenty of stuff there that make up protons and neutrons, not a lot there to make up a electron. So the neutrons and protons live in the nucleus, and they live very close together in the nucleus. I mean, it is a massive space, a very tiny, tiny space, but has all the mass of the atom pretty much in there, except for this tiny amount in the electron. Now, the electrons fly around in a cloud outside that nucleus, okay? Now, that cloud takes up many times much volume than the protons, than the nucleus does. So, basically, these electrons that are flying around out there with almost no diameter at all, okay, flying around this huge cloud with nothing in between them. I mean, absolutely empty space in between them. Nothing else there. All the mass is located in the nucleus, and these almost massless electrons are taking up this huge volume with almost nothing else there. And I can remember my older brother coming back from Georgia Tech after he had taken his first physics course there. I think it was the first quarter of his sophomore year, and he said, all of everything is nothing, meaning that most of the space occupied by any atom in the world is occupied by empty space. All the mass is located in a tiny little area, and all the space around it, all it has in it is a few electrons flying around with almost no mass themselves, and all the rest of it is absolutely empty space. Okay? Rather strange makeup. Okay? Now, just talked about the nucleus. There is a figure at the top of page 312, if you've got your books. It shows, and let me go back to the previous. I guess I'll stay here. Shows a hydrogen atom. Now, hydrogen atom, most hydrogen atoms, the vast majority of hydrogen atoms just have a single proton. Single proton. And flying around that proton is a single electron. Most hydrogen atoms have no neutrons. Once every about 10,000 or so, you'll find one with a single neutron. And maybe once every million or so, you'll find one with two neutrons, okay? But all the rest of them are single protons with a single electron. Now, that electron doesn't fly in an orbit like is shown in the book. It's just all over the place. Anywhere it wants to be around that proton. Okay? That's hydrogen. The next one they show is a carbon atom. Okay? Now, a carbon atom trying to recall if this book has a periodic table somewhere in it. Most of the time, physics books are not good about having periodic tables. Those are in chemistry books. I don't see one. But if you were looking for carbon, the top row you have hydrogen with one proton, one electron, helium, two protons, two neutrons, two electrons. Then you have lithium, beryllium. Then you come over here to boron and carbon, okay? So 1, 2, 3, 4, 5, 6. It has 6 protons, 6 neutrons, and 6 electrons. And that's what's represented here. I hope they got the numbers right. Yeah. Okay. Now, as I said before, you have hydrogen here, helium there. That's the first row. The first row only has 2 elements in it, hydrogen, helium. Helium's outer shell has 2 electrons in it. That's absolutely full. It will not take any more. Helium doesn't react with anything. It's completely inert. It's called a noble gas. Hydrogen reacts with just about anything. It gives up electrons, it shares electrons, it does whatever. You hardly ever find pure hydrogen, okay? Hardly ever, okay? Then you go over to lithium. It has 2 electrons in the inner shell and 1 electron in the outer shell. It's real easy for it to lose that 1, okay? Beryllium has 2 in the inner shell, 2 in the outer shell. It sometimes will lose the 2 in the outer shell and become positively charged ion, or it will combine. They're both very reactive. You come over here to boron. Boron has 3 in the outer shell, 2 in the inner shell, 3 in the outer shell. It's very reactive, but it mostly shares those electrons. Carbon over here, and the one that you see in the book, 2 in the inner shell, they don't go anywhere, they just stay right there. There's 4 in the outer shell. Those combine very readily, mostly by sharing. They don't lose them or gain them, but they share. If we go back here, these are our carbons here, okay? And notice every carbon has 4 links. Every carbon has 4 links. Each link represents 1 electron, okay? Now, these 2 here combine with this 1 oxygen that has 2 outer shell, so they get paired up. This combines with that, with that 1 hydrogen. That's all hydrogen can share with, and it shares one with another carbon. It shares with an oxygen, a single, carbon, a hydrogen, and another carbon. So all the way around, they have, each of those electrons shares with some other electron. So they wound up with 8 shared electrons in their outer shell. That's where the atoms are very happy, having 8 in the outer shell. Except for helium, it only has 2. Okay? And that's why they combine like they do. Okay, then we get ready for this slide. Now, we're beginning what this chapter is based on, the differences between solids, liquids, and gases. Okay? Now, what makes a solid is that all of the atoms are arranged in a fixed order, a fixed regimen, a fixed plan, scheme. They get there and they're set. And that's why the solid is a solid. It doesn't move, it doesn't change shape, it's fixed in place. What can the atoms do? Nothing but vibrate. Okay? That's all they can do. Just little movements, but they don't break their bonds. Okay? Now that's not a very revealing picture of a crystal structure, but all solids, to be a solid, technically you need to be in a crystal structure. Now, what about liquids? Liquids have this tendency to stay close to each other, so they're fixed in their proximity to each other, but they're not bound in position. So they can slide past each other and do whatever they want. That's why liquids take the shape of any container. Okay? They have a fixed volume, they stay close together, but they can take the shape of any container. A solid is a solid. No matter what container you put it in, it still has its own shape. Its own shape, its own volume. Okay? So the liquids are free to move around. Okay? Gas molecules, they don't even notice each other. Not only are they free to move past each other, they don't even hang close to each other. Okay? Let's just imagine that I had a bottle of ammonia, and I was going to open the lid here, not tell y'all, and say, oh, I've got to go out of the room for a minute, and I were to leave the room. And that bottle of ammonia would sit there, and after a while, Jalen, what did he leave in here, you know, and then Joe and, you know, all the rest of you, after a while, you would all sense the ammonia was here. Why? Those ammonia molecules, the gas that's escaping from the bottle, would just take up the whole room. Okay? The liquid stays right there, you know. The bottle, the solid, stays in its right shape there. Okay? So the gases just move anywhere they want to. No proximity to each other. And every now and then they'll collide with each other. They're far more frequently here than you normally see. But most of the time they're just floating freely. So that's basically your difference between solids, liquids, and gases. Now, how do you make some solids into liquids? Maybe not all solids you can do this to, but most of them you can. How do you make a solid into a liquid? Heat it up. Very good. When you heat it up, these vibrations get more and more and more, and finally the bond breaks. And when the bond breaks, the cradle will fall. No, that's a different topic. They become liquid. Now they move close to each other, but they're no longer attached. That's what changes from a solid to a liquid. How do you change a liquid to a gas? Actually, that's not far, but usually they say in that shape. Say again? Add more heat. Exactly. When you add more heat, then you break this sort of what you call the cohesion bond, that bond that tends to hold them together, and now nothing's holding them together. They're flying freely. Now, what they didn't mention here, and I'll just mention it briefly, is there is a fourth phase of matter. They used to call them states of matter. Nowadays, they like to call them phases of matter. Anyone know what the fourth one's called? Some of you may have TVs with this in their name. Or not. Plasma. Okay, now what makes a plasma is they're no longer atoms or molecules. They're now ions. And the ion is a charged particle. See, all these represent neutral particles. Neutral particles in a solid, neutral particles in a liquid, neutral particles in a gas. What a charged particle is either it has an extra electron that makes it a negative charge, or it's lost an electron, which makes it a positive charge. Those are ions. Okay? Now, how do you reckon we get ions? It's your line. Add more energy. Exactly. Add more energy. Okay? Now, can you think there are any ions, plasmas in the room today? In our room? Right here? Actually, there are. In these tubes. Okay? I don't know if you've looked at what a fluorescent light is, but they'll have a big box up in there somewhere called a ballast. Basically what that big box they call the ballast is, that's very alliterative, is a capacitor, a big capacitor that builds up charge. And it builds up charge so there's a big potential difference between the two ends of that light tube there. Big potential difference between excess of electrons on one side and deficit on the other side. So the particles in there get ionized, okay? And then they fly back and forth to one to another to try to balance. And when they fly past, have you ever seen one of these tubes that broke? How it has that white powder inside? That's called a phosphorescent material, okay? Now what that does is when an ion goes by pretty close to it, it makes the electron in that powder, it energizes it and it jumps up a level. Remember I said there were levels here and the level there. There's levels of these electrons, and when it jumps up a level, that's because it picked up energy. But then when the ion goes by, it loses that level, that energy, and it drops back down a level. And that measure of the drop, decrease, that gives off the photon of light. That's what's happening. Light is given off when the electrons fall back down to the lower level. So that's what a plasma is. Now, In the universe, now this is a question I can't prove as an answer, but in the known universe that we see and observe, what you think is the most common phase of matter? Solid, liquid, gas, or plasma? Second? Gas, is that what you said? Not a bad guess. Okay, let's just think about our solar system. Maybe not the whole universe, our solar system. Would you say gas there too? What would you think? Plasma. Because the sun is so, if he was in here, Jalen would say, has so much heat, is so hot, has so much energy that just about the entire volume of the sun is a plasma. And the reason I picked our solar system, the sun, if you were to add all of the planets moons, all of the asteroids, all of the comets, and all of the other stuff that might be out there in our solar system, add them together, the sun still has like 700 times the mass of all the rest of them put together. So the sun is by far the most massive thing, in fact, occupying most of the matter in our solar system, and it's mostly plasma. So I think it's okay to extend that to the universe. And so all the stars out there, massive. Our sun is just an average star. There's tons of stars out there way bigger than our sun, way hotter than our sun, way more plasma. So I think that's probably safe. But that's not covered in the book, so you don't need to know that. Okay. Let's move to properties of solids. And it's going to be a while. Oh, boy, Deidre, if she were here, she would be on my case. I'm supposed to open this too. Okay. Now, I've already used these two terms before. I know I've used one of them. I may not have used both of them. Okay. And the first of these terms is cohesion. Let me get my pen activated. Anyone make a guess of what cohesion means? To cohere. Yes, ma'am. Thank you. Okay. I asked it to be sent to her. I don't know why it wasn't. They sent it to her email address, but maybe they messed it up.
Email is not working. We try our best to fix it. It's not working, and she sent it down.
Oh, okay.
And that's why she's been sending you an email. I've been sending you an email.
Okay. Well, I tried to send it to her days ago, but I'll try again.
Okay. The email that she sent you one today as well. And I
Pardon me?
Send it to me to the video.
Oh, well, okay. I can't do it now. I don't have it with me. Okay. All right. All right. Okay. Anyone have an idea what cohesion is? What does the prefix co usually mean? Second? Combine. Yeah. With, co, with, okay? Hesion. Think. What's the tannish kind of tape that we put on the wall? That's supposed to not pull paint off the wall. Second? Okay. Painter's tape? Yeah, that's usually bluish and stuff, but this can be tan too. I'm thinking adhesive tape. Adhesive means sticking. So these stick together. Things that stick together, cohesion. Similar things that stick together. Okay? Cohesion is the force of attraction between like molecules. Okay? Remember when we talked about water, how the molecules stick together like crazy. It should be a gas, but They stick together so closely they don't become a gas, they become a liquid, okay? Water molecules stick together like crazy. That's cohesion. But mercury molecules stick together even more than water, okay? They cohere very, very much. The sticking together of like molecules. Adhesion, on the other word, is the forces of attraction between different, okay? And this is where adhesive tape comes from. Adhesion. Because it sticks tape to wall, you know, it sticks note to board, you know, it sticks things that are unlike together, okay? Now, water also adheres very good too, or very well too, however you say that. You can tell that by, you put water in a tube, and it's going to climb the walls of the tube. It sticks together and it pulls more water up. Anyone know what that process is called, pulling water up a very small tube? It happens in your very tiny blood vessels. What do you call those? Very tiny blood vessels. Capillaries. Have you heard that before? You never heard of capillaries? Okay. It's called capillary action. Okay? I try it sometime. If you get some of those really tiny little straws like they use for coffee, find some that are clear, stick them in a liquid, water will be fine. Stick them in there and you'll see the water actually goes up the little capillary tube because the adhesion is pulling the water up the walls and then the cohesion is pulling the water up with the other water. And that's what happens in capillary tubes. Are any of you in the medical field? Okay. Have you ever seen when they stick and you get a drop of blood and then you get this capillary tube? What happens? It just sucks the blood right up there. That's capillary action. Okay? That's what we mean by capillary action. Okay? So that's a combination of cohesion and adhesion. Okay? The next term we get to here is tensile strength. Now, how about that word tensile? T-E-N-S-I-L-E. That's a pretty ugly E, isn't it? Getting worse all the time. What do you think tensile strength is? Well, what word do you almost see in tensile? Second? I can't hear. My hearing is so terrible. In tensile, in this word here. T-E-N-S-I-L-E. T-N-S-I something else. Tension. Okay? What is tension? It's pulling in a linear direction. Okay? So tensile strength is strength in a linear direction. Okay? For instance, let's say we had a game of, what do you call that? Second? Tug of war, exactly. And you had, both sides are pulling on the rope, you know, trying to pull the thing over the center part. That is tension. You're putting tension on the rope. Okay? So tensile strength is in a linear direction along the rope. Okay? The tensile strength of a solid is a measure of its resistance to being pulled apart. That's its tensile strength. Okay? As you can imagine, the tensile strength on railroad cars, those hooks, the connectors on the railroad cars have to be pretty strong because those are pulling heavy, heavy loads, okay? You want the tensile strength to be very high there, okay? Now, the tensile strength of a rod or a wire is found in also hanging pictures, okay? You know that wire or the rope or whatever you have, you want it to be strong enough to hold the weight of the picture, right? So, tensile strength, okay? The tensile strength is a ratio, meaning something divided, the force required to break the rod or wire I can't write. Divided by the cross-sectional area of that rod of wire or wire. Okay, so the tensile strength is the force needed to break it divided by the cross-sectional area. So you make a bigger cross-sectional area, generally you're going to have a bigger force to break it if the tensile strength is equal. Okay, so if you are hanging just a very small picture, like maybe something as light as this piece of paper, and you're going to hang that from the corners, you know, and stuff, you would only need a very small wire. Okay, now if you're hanging the clock, I wouldn't want to do a very small wire with that because I don't want the clock to fall. If I'm hanging the screen here, I'm going to use something a lot heavier than that, bigger cross-sectional area, if it's all the same material and with the same tensile strength. Okay? Now, another topic they mention here under solids is hardness. Okay? Now, in many things, such as minerals and stuff, I was just teaching this afternoon in my physical science class, we use the Mohs hardness scale. Diamond being the hardest, talc being the softest, and there's 8 things in between. Okay? This book is talking about the Brunel method, named after Johann Brunel, is a common industrial method used to measure hardness of a metal, strictly about metals. So the Brunel number measures hardness. Okay. It's also a ratio, and that's the ratio of the mass placed on the object divided by, and that's in kilograms, by the way, that's mass unit, okay, divided by the surface area of the impression. Okay, of the impression. And that's in millimeters squared. A very, very small thing. So that would be, say a machine is used to press a 10 millimeter hardened chrome steel ball with the same force as equivalent to 3,000 kilograms into the metal being tested. The diameter of the resulting impression is used to measure the hardness. Okay? Now, this isn't quite the same thing, but when I was in the Navy, we were having what they call a in-serve inspection, and they were getting ready to go in the yards, and they wanted to check out all the different things on the ship. And the anchors up front, big, heavy. I mean, the anchor itself was, I don't know how many tons, enormously heavy. And each link in the anchor chain was many tons. I don't know how many tons. Each link. And it had, I don't know how many links. I mean, big, long chain on a sword down below deck. And they were wanting to test the manual anchor windlass brake. Okay, not the hydraulic one that we normally use, but the manual one. A big wheel that some bosun mate had to turn. And we were testing this. No one had used it probably since the ship had been built, you know, and yet they were requiring us to test this. Well, I was, as the assistant first lieutenant, I was down on the deck, had a phone talker next to me, and the people were all there, the inspectors were there, and my crew was there, and they were doing the thing. So I was communicating through my phone talker to the bridge to let them know. So do 15 fathoms. Well, they let 15. Every 15 fathoms, they have a color. Green, orange, and then red. read was 45 fathoms into the water. You didn't want to go any more than that. That's more than enough. You stopped it then. Well, they said test it at 15. Well, we saw the green link go by, had the bosunmate just turning like crazy, great big wheel. He finally got it stopped, but it took quite a few more links before it went by before he got it stopped. And, well, this isn't really working too well. Do we really? Yeah, we need to do 30. So we released it and let it go. Well, it was no time when 30 went by again, because think of this, all this more weight was down there in the water pulling it, so it was going faster and faster. So he cranked and cranked and cranked, and finally got it stopped at 30 and said, look, this is, he almost didn't get it stopped here. Do we really? Yeah, we need to do 45. So they released it, and then 45 just flew by in no time because it taken so much. Well, stop it. And he was turning as madly as he could, as much as he could put in it. Big, strong guy. It went faster and faster and faster. It wasn't even slowing down. And finally, all that weight down there, it broke. And they do this on purpose. In the Navy, they have what is called the weakest link. And that's right before you get to the bulkhead. It's a much weaker link of chain. So if you did lose the anchor, then it doesn't pull the whole bulkhead out because it's that heavy. And you don't have a hole in your ship. You you just lose the chain. And that's exactly what happened. The weakest link broke. That thing came flying out of the hose pipe below deck and went whipping up and went through a brand new antenna we had just put up for what now we call, back then we called it satellite navigation. Now we call it, what do you do on your phones? Second? Second? Yeah, GPS. Yeah, that's what we call it, that GPS. We called it satellite navigation back then. Y'all didn't have it then, we did. We'd just gotten it, just learning how to use it. Brand new antenna. It just tore it apart. And, I mean, there was rust and dust flying everywhere. And just that last chain came up, flipping back and forth, and down the anchor hose pipe, going into the sea. Well, I looked around when the dust settled. My phone talker was almost over the ship. I mean, he was straddling the side. He was ready to fall into the water if that thing came too close to him. I helped him get back on board. And then I happened to glance down at the deck. And the deck is probably, I'm guessing, about a 6-inch thick metal plate. 6 inches thick of metal. And it had an indentation the size of a big serving bowl. And it was about 18 inches from where I was standing. And I went, even though those are steel-toed shoes, that wouldn't have done me a bit of good, And I wondered if just that little bit of hitting that antenna was just enough to deflect it. It was sort of scary. I mean, at the time it was just happening too fast. But anyway, so when I read this, talking about the surface area of the impression, that was a big surface area. You wouldn't have measured that in square millimeters. Okay, but that's hardness for metals. Another term they have here is ductility. Anyone want to make a guess of what ductility is? How ductile something is. What would that be a measure of? I'll give you a hint. It relates in some small way to tensile strength. How ductile something is how the property of a metal that enables it to be drawn through a die, which is a very small opening, drawn through, meaning pulled through, to produce a wire. Okay? So in other words, how easily it is to stretch something into a wire. Okay? The diameter is decreased and the length is increased. So it would sort of be like, this is a really lousy example, but have you ever grated cheese on a grater? And when you do that, you're actually cutting the cheese, But if you can imagine sucking it through there, pulling it through, that would be ductility. Of course, cheese would break. Wires hopefully don't. Copper is very ductile. Gold, not so much so. Silver is pretty brittle, so it's not very ductile. So that's what we're talking about there. Okay? Now here's another one. Malleability. M-A-L-L-E-A-B-I-L-I-T-Y. Anyone make a guess of what that is? Well, say again? Yes, think of this as a mallet, okay? You're hitting it with a mallet. How thin can you make it become, okay? Malleability is the property of a metal that enables it to be hammered or malleted and rolled into a sheet, okay? I can think of one metal that's very, very malleable, and you use it probably pretty frequently. Say again? Say again? I don't know if it'd be used on a phone. I'm trying to see. What's that you got on the desk right there? Aluminum foil. That's the metal that you can hammer and roll into very thin sheets. Actually, gold is probably even better. We just don't do it very much. But have you ever heard of anything called gold leaf? Yeah. And you can have a very tiny amount of gold and put on something like plaster or something, and it looks like it's pure gold, but of course you've just got a very thin aluminum foil, gold foil on it, and yet it looks really rich, doesn't it? Okay? Elasticity. Okay? What in the world would elasticity be? What do you think of when you think elasticity? Stretching. That's what we usually think of. Actually, it's almost the inverse of it, though stretching has to do with it. It's returning to its original shape after it's been stretched. That's what makes something elastic. And that's really what we want too. My elastic band, I want it to return to its original shape. I don't want it to stretch and then not go back. Otherwise, it doesn't do me any good. Okay? So, elasticity is the measure of a deformed object, once it's been stretched or something, ability to return to its original size and shape once the outside forces are removed. Okay? These balls that people use to take stress away? They play with them like this all the time. You can press and do anything you want to. When you release, it goes right back to its original shape, right? That's very elastic, okay? You want most of your things to. I know you're a volleyball player. The volleyball itself is pretty elastic because when you really cram it, if you were to look at the slow motion of that, your hand, the ball wraps around your hand bends back, but then as soon as it leaves your hand, it pops right back to the original shape. That's where it gets the speed for doing that. If you've ever seen a slow motion shot of a golf club hitting a golf ball, as hard as that golf ball is, it actually flattens out against the face of that golf club momentarily and then springs off, and that springing off is what sends the golf ball flying. Baseball bat, okay? That baseball will actually, if you looked at a slow motion shot of it, you would see it almost wraps around the bat a little ways, not much, and then pops right off of it. Tennis racket, tennis ball, even more so, because tennis balls are pretty soft. They actually almost flatten out against a tennis racket, especially someone like Serena Williams swinging it, and the tennis racket also bulges backward, and then it comes right back, and that gives the velocity. So that's elasticity. When it is deformed, its tendency to go back to its original shape. Okay? Now, we talk about there with elasticity something called the elastic limit. Okay. There's materials. I'm not going to do it, but I think you could imagine that it could be done. Okay? Every time I hit on this leg, even though I'm not doing much to it, it does bend a little because you can actually see it vibrate a little bit. It bends and comes right back. Okay, now if I had a heavy enough sledgehammer and hit it hard enough, it would pass its elastic limit and it would actually bend and not come back. That's its elastic limit. You can increase the hit, increase the force, and as long as it comes back, you're within the elastic limit. Once you exceed that elastic limit, it doesn't pop back. Okay? Now, do y'all remember the old Saturn commercials, the car? Probably not, way before your time. It was a brand new car actually made in Tennessee, somewhere in Knoxville or somewhere up in Tennessee. And their claim to practicality was the kid throwing the ball against the car, throwing it somewhere and it actually hits the side of the car, but then the car pops right back. Without, if it stayed dented, that's not elastic. If it pops back, that is elastic. And that's what they had in their ads. That was supposed to make them better than other cars. They're no longer around. So we'll leave that. So the elastic limit of a solid is the point beyond which a deformed object cannot return to its original shape. In that case, the spring's molecules were pulled far enough apart that they don't pop back. They don't go back together. All the king's horses and all the king's men. Right. Okay. Now let's see. I can't remember. Let me. Nope. Nah. That one. Okay. That's where we want to be. Could have gone another place. All right. Here's a spring before you stretch it. Okay? Now, the more you pull, the more it pulls back, right? Now, if this spring had some spaces between it, you could also press it together, and then it pushes back. So the spring is always trying to do the opposite of what you're doing to it. Okay? Now, if the spring is pulled near its elastic limit, you release it, then it's going to come back. As long as it hasn't exceeded its elastic limit. Once it's exceeded, release it, and it doesn't do anything. It stays sprung, okay? And you've probably seen or experienced that before, too. I don't have a rubber band with me today, but you pull it a little bit, it usually goes right back to its original shape. But you can easily imagine stretching it a bit too far, and it doesn't do anything else. That's when you've exceeded its elastic limit. But if you stretch it even further, much beyond the elastic limit, it actually fractures or breaks. And you can easily imagine that in a rubber band, right? Pull it too far, and it's not that it passed its elastic limit, it's past its fracture limit, and it actually breaks. So that's that. Now, here are, I want to say two terms, but I actually only see one of them. Yeah. All right. Let me just make sure they don't have this on the slide. No, not yet. Okay. Here's a term, because I've changed. Okay. Stress. Okay, now we all think we know what stress is, right? But in terms of physics, what this is another ratio, and it's a ratio of an applied force to the area over which the force acts. It's the ratio of applied force, goodness gracious, I can't read right, applied force to the area over which it acts. Okay. Now, seems like I already did this one for you, but maybe not. What is my force right here? What's one way to measure my force? Did it yesterday morning. Stepped on and read the little numbers. Second? Yeah, my weight. That's my force, right? So that would be an applied force. Okay? Now, I was dancing with my darling, okay? And she stepped on my toe. I got it in the way. But she was wearing sneakers, okay? Okay. Applied force was her weight, but the area over which it was applied was the sneaker, okay? And that's not a huge amount of stress. Might hurt a little bit. But I was dancing with my darling, and she stepped on my toe again, but this time she was wearing spike heels. Any difference? Applied force was exactly the same. She didn't weigh any more, but the surface area was much less, so the stress was big times more, okay? So that's what we mean. Stress is the applied force divided by the area over which it acts, okay? We'll have another name for that coming up just momentarily. And the symbols for this is S is equal to force over area, okay? Now, in the SI units, what is the measure for force? Anyone know? Second? Okay, and what is that in the SI units? The unit. Newton. Okay, and what area do we use in SI unit? Area is a length times a width. What do we usually use to measure lengths and widths? From your ear to your fingertip, approximately. Height of a doorknob. What's that? The verb comes from to measure. Meter. Okay? And since it's length times width, that would be Newton per meter squared. Now, that's a very, very small unit. Okay? The reason is a Newton is a small unit of force to begin with, but a square meter would be about, you see the door back here? I'll open it back, but I want everybody to be able to see it. A square meter would be about from the floor to here to there. That's about a square meter. That's a huge area. And 1 Newton of force on that is a very tiny stress. Very tiny. Okay? Extraordinarily tiny. Okay? But a Newton per square meter has another name. Does anyone know what it is? It's a Pascal. P-A. Pascal. Named after Blaise Pascal, who was a French physicist, scientist, mathematician, quite a character. Okay? Actually, also a theologian, believe it or not. I didn't realize that. He actually invented a calculating machine, one of the earliest computers, you might say, called the Pascaline. Okay? He later invented the barometer. Okay? Hydraulic press. Okay? Syringe. He formulated the modern theory for probability. Now, I think I know the reason he did that last. He and a bunch of his buddies were big gamblers. So they figured out if they understood probability, they could give them an edge in gambling. Not the maybe the best thing going. But anyway, that's the Pascal. Now, because that's such a tiny, tiny amount of stress, Newton per square meter, we usually use a bigger unit And we'll get to that in just a minute. In the SI and the U.S. customary, what do we use to measure force? What's the unit for force? Anyone know? What was the force of me standing on the scales? Weight. And what do I measure weight in? Pounds. Okay, so in U.S. customary it's pounds. And then what is our unit for areas? Actually, we have several. And if we really want a big unit, that would have a small denominator, and that would be square inches. Pounds per square inch. That actually has an abbreviation in itself. Anyone know what that's called? Pounds per square inch? None of you put air in your tires, do you? PSI. Always on the wall of the tire, it'll tell you what the recommended PSI for putting that in, pounds per square inch. Most days today, most tires today actually will first have how many kPAs, kilopascals, 1,000 pascals, and that's approximately the same as a pound per square inch. It's not the same, but they're in the same ballpark. Okay, so those are the common units there. And by the way, what I didn't say, I probably should have, all my illustrations were, this force is always perpendicular to the area. Okay, so it can't be a glancing force, it has to be a vertical force or whatever, perpendicular to the surface. Okay. Okay. Now, here we have two identical bricks on this table here. Which of these bricks, and the identical bricks, meaning they have exactly the same mass. They have exactly the same dimensions. 16 centimeters by 8 centimeters by 6 centimeters. Identical, 16 by 8 by 6. Identical mass, identical everything. Which of these is putting more stress on the table? Any of them? Are they the same? Same mass, same overall dimensions. Either of these putting more stress? Yeah, the one standing up because it's on a smaller area. That'd be like the spike heels, you know. So this has more stress on the table than that. Okay? Another word we usually use for that, and I don't know why they don't say it, I've already said it, pressure. Also measured in pounds per square inch, newtons per square meter, pascals, kilopascals. Okay? They're calling it stress. It's also called pressure. Okay. Then they show the woman with the flat heels and the spike heels, and we've already been over that one. Let's see if we have the picture. No, we don't. I don't know. If Deidre was here, I'd go to the other slide, but since she's not, I'm going to cheat and stay on this one. Is that okay? If a 160-pound woman, what's that a measure of? 160 pounds, what does that measure? What does it sound like it measures? Weight, and weight is also a form of a force. So that's your force due to weight. Okay, so there's your force. Rest her weight on a 4 square inch heel. So her 4.0 square inch heel. What's that a measure of? Four square inches. Square inches measures what? Area. There's your area. What is the stress from that? Not that hard. Anybody? 160 pounds divided by 4.0 square inches, and that would be 4 going to 16, 40 PSI, pounds per square inch. Okay, 40 PSI, pounds per square inch. Okay? But if she rests her weight on pointed heel of 1/4 of a, so let's do the second part of this. Let's do a different color. What color you want for this part? Green? Is that what you said? Okay, let's do green. If she rested it on a 1/4 square inch, if I can find it now, I think that's what it said. Yeah. If now her area was 1/4 of a square inch, everything else is the same. What's the stress now? 160 pounds divided by 1/4 square inches. Well, a couple ways you could do that. When you're dividing by a fraction, you invert and multiply. So that would be 160 pounds times 4 over a square inch. You invert and multiply, and this would be 640 pounds per square inch, as opposed to 40 pounds per square inch. I say that's a bit more stress, wouldn't you? As in 16 times more stress or something like that. Okay? Then they do the same type thing with SI units. If a 60, can I erase these? Deidre would be wanting me to be on a difference, on a clean piece of paper. Okay. For a 65 kilogram woman, let me go back to dark black if I can find it. Okay. 65 kilogram. What's that a measure of? What does that measure? Second? I don't think so. Kilogram measures mass. Okay. 65 kilogram woman rests her weight on a 25 square inch heel. Square centimeter heel. That's in area. What is the stress? So how do we measure stress? What's the formula for it? Force per unit area. Well, we don't have a force. We have a mass. How do we get from mass to force? Absolutely. Multiply the force due to weight, that's what we're dealing with, is your mass times the acceleration due to gravity, which would be 65 kilograms times what? 9.8. You can put the 0 if you want to, meters per second squared. And so on, multiply that out and see what you get. 640 something, 630 something. $634 maybe?
637.
Huh?
637.
637. Okay. 637 what units? Nope. Kilogram, meter per second squared. What's that measure? Newton. 637 newtons. Okay. Now, we have a problem here at Houston. The 25 square centimeters, we need to get that into square meters. Okay? So I'm going to erase the A for just a minute. Is that okay? I may do it for more than a minute. I'm going to put my A on the other side. So we need to get blank blank to get this in terms of meters squared. Okay? So how do I do that conversion? Notice I have two blanks. The first blank is for numbers, the second blank for units. What do we put in their place first? Always put the units in their place. So what unit is going to go where? Between centimeter and meter, one goes on top, one goes on bottom. Meters on top, centimeters on the bottom. Now I need a conversion between meters and centimeters. How many meters in a centimeter, or how many centimeters in a meter? 100 which? 100 centimeters makes 1 meter. Absolutely right. That's like 100 cents makes $1, right? But we don't have centimeters and meters. We have square centimeters, and we're trying to get the square meters. So we're going to have to square the units, and we also square the numbers. And 1 squared is 1. Thank you. Okay. Right? What is 100 squared? Anyone know? Basically, you double the number of zeros. 1, 0, 0, 0, 0. So that's 10,000 square centimeters makes a meter. The square centimeters go out. So basically, you take the 2.5, divide it by 10,000, which is moving the decimal 4 places to the left. 0.0025. Pretty small number, right? So to get your stress, the force, you said 637 newtons divided by your area now is 0.0025 square meters. And that's a huge number. What is it? Anybody got it? 254,800. And that would be newtons per square meter. Anyone know what a shortened name for that is? Newton per square meter is a Pascal, exactly. Now, 254,800 is too many digits. Here we have at most 2, here we had 3, but just about everywhere we had 2. So let's round that to 250,000 pascals. And if I wanted to use a smaller number but a bigger unit, that would be what? 250 kilopascals. Okay? And what the book actually uses is 2.5 times 10 to the how many? 1, 2, 3, 4, 5 to the 5th pascals. That's another way you could write it. And that's how the book did it. Or they also put 250 kilopascals. I like 250 kilopascals because a lot of things are measured in that. All right. So remember, a pascal is a very small amount of stress, also called pressure. Okay, for instance, you remember back just a few minutes ago when I closed the door? You know, to let you see what a square meter was? I probably increased the pressure in this room by several pascals. Did y'all notice the pressure beating on your eardrums? No, because it's such a tiny amount of pressure. If I opened the back, it changed it the other way. No, you didn't notice a thing. All right. Now, Now, what if she had a pointed heel? So we'll go back to green again, or do you want something else? Green okay? Okay. Go back to green again. This time she rests all her weight on a pointed heel, and this pointed heel had an area of 1.0, if I can find it here, 1.0 square centimeter. Okay? Well, we still need to do our same conversion, which basically, remember, is just moving the decimal 4 places to the left, so that would be 0.00010 square meter. Okay, that's all we had to do, move the decimal to the left 4 places, and that's 1 and then 3 more zeros, so that's what it is. Now your stress is force 637 newtons, this time divided by 0.00010 meters squared. Okay? Well, basically all you have to do here is move the decimal 4 places back that way, which moves this decimal 4 places back this way. Okay? And that gives you 6.4 million pascals, or 6.4, oops, messed up, get my pen back, eraser back, 6.4 times 10 to the third kilopascal. Okay, so in other words, 6,400 kilopascal, whereas before it was 250 kilopascal. So quite a bit of difference, 6,400 kilopascals. All right. Now, let's think back. Remember we were talking about tensile strength, and we used the example of tug of war. That's exactly what the next picture is showing. This time we're talking about tension. Okay? And this is going to talk about tension as well, going the other way. And there's another. Okay? So tension is a stress caused by two forces acting directly opposite each other. Now with a tug of war, why is that doing that? Okay. With a tug of war, get back to black. Get back to black. Okay. Your tensions are this way and that way. But it's still opposite each other. That's tension. Okay. Compression is kind of the reverse of tension. Okay. Compression then, so this is tension. Okay? Compression is when they're opposite each other, but now toward each other. Okay? And there's an example of compression, and also this one. If you're pressing on both ends of something, forces coming from opposite directions, but toward each other, as opposed to tension, which is away from each other, then this is called compression. You tend to push this rod closer together, push the pylons down, whereas this is pulling the rope or the thing that you use in a tug of war further apart. Okay? And this picture here is a column under the New Clark Bridge crossing the Mississippi River. That's in compression. And the figure to the side shows the illustration of that. Now, so tension is opposite directions away from each other. Compression is opposite directions toward each other. There is another type of force that we deal with in solids, and that's called a torsion. Okay? Let's see if we can get a better picture of that. This is what that looks like. The forces are opposite each other but displaced from each other. So you've got a twisting force in it called a torsion, which is similar to the word torque. Okay? Because the forces have a distance between them. Okay? They're in opposite directions but offset at a distance between them. So this gives you a twisting kind of motion. The illustration is do it on a book like this, and you see it deform itself. You're pushing one way, friction's on the other way, and this is the illustration of that. Now, here's another way of a torsion, and this is a wrench that your force is this way, the object of your force is there, so again you have a distance between your force and what you're trying to do with the force, go into the wood, okay? And this is a twisting kind of force, excuse me, and that's also a type of a torsion, okay? In other words, torques. Now let me describe to you what a torque is. And we talked about this when we were talking about work, remember? Foot-pounds. That's when the force is in the same direction as the displacement. Here your force is perpendicular to your displacement. This is a torque, which is a vector quantity, not a scalar quantity. Work is a scalar quantity, torque is a vector quantity. Okay? Now, here's another example. The twisting of a bolt in one direction is counteracted by the force of the wood resisting the turning motion. So that's what you're measuring is the torque. And the symbol for torque is that little, it's a Greek letter for T, which is tau, and that's the symbol we use for torque. It's a vector quantity. Now, another thing, and I've given this example in here before, but I was walking on it in the example. This one's actually sitting on it, which is a lot safer. And this is a bending force. It consists of both tension and compression stresses. Okay? Because what's happening there is the bottom part of the board is having a tensile force on it. The top part of the board is being compressed. So you have two types, and actually they kind of create some type of a torque themselves in the twisting nature of it. But that's not the important thing here. This is what, in a bend, you've got tension and compression. Okay? All this, blah, blah, blah. Okay? There is a try this activity. If you want to do this at home, you certainly are welcome to. This is talking about stresses on foam, which is a very unstressful material. But let's finally get to a problem, okay? And there's the stress that they said try at home, okay? And there's elastic limit. So I think probably what we ought to do is escape from here and go to this slide. Okay? All right. I guess some people still have to go at 5:30, huh? Okay. I'm glad we're recording so they can follow later. So let's do example 1 on page 320. A steel column in a building has a cross-sectional area. Okay, let me get my pen back. Steel column in a building has a cross-sectional area of 2,500 square centimeters. So the cross-sectional area is 2,500 with the bar over the first 0 square centimeters. I never would have thought of measuring cross-sectional area of a building in square centimeters, but I guess okay. It supports a weight of 1.5 times 10 to the 5th newtons. So this weight is the force due to weight, and that's 1.50 times 10 to the 5th newtons. Okay? It says find the stress on the column. Well, first thing we got to do is get that square centimeters to square meters. How do we do that? You want to go through the whole thing, or do you remember the shortcut? Okay, and what was the shortcut? No, probably. Second? Yeah. Okay. What you do is move it 4 places to the left. Why 4 places? 100 centimeters in a meter, squaring them, that's 10,000, 4 zeros, so move it for, so this is 0.250 meters squared. Okay, now we can calculate the stress. S is equal to F over A, and your F here was 1.50 times 10 to the 5th Newton divided by, you can leave it like that if you want to, 0.250 meters squared. And what would that give you? I would move decimal like that. 25 will go in 156 times. 6.00 times 10 to the 5th, I guess. Newton per square meter. And what's another word for Newton per square meter? What's that? PA, Pascal. Okay. 6.00 times 10 to the 5th Pascal. But if you wanted a smaller number, bigger unit, what would that be? 600 kilopascal. Okay, because you'd move the decimal 3 places to the left. Okay, because kilo is 1,000, and that would be out of 5, you have 2 left over, so it'd be 600 kilopascal, and that's exactly what they got. All right. Here's another character named Robert Hooke. Pretty famous chemist, physicist, English. He came up with the law of elasticity, Hooke's law. He invented the balance spring for watches, worked with and made important observations on the telescope, microscope, formulated the theory of planetary movement. He was English, 1630s to 1703, something around there. If I'm not mistaken, a little bit preceded that guy named Isaac Newton. And Newton was not an easy person to get along with, and I think he and Hooke had sort of a falling out. Newton was absolutely incredibly brilliant. Hooke was too, a smart man, but goodness gracious, who could stand up to Newton? And Newton just, I think, ate him up. You know, they weren't happy. So Hooke's law says the ratio of the force applied to an object to its change in length, resulting in this length being stretched or compressed by the applied force, is constant as long as the elastic limit has not been exceeded. So basically, the shorthand for that, you want me to go to a clean page? Okay, let's go to a clean page. The ratio of the force to the change in length, delta L, delta meaning difference in, that's equal to a constant. And that constant depends on what kind of metal, material, spring you happen to have. Okay? Like the coil springs in your car, that's an enormously large K. A slinky, an incredibly small K. So it all depends on that. Okay? So there's Hooke's law. Now, most of the time I express it this way. F is equal to K delta L, which most of the time we say is KS, KX or something like that. The change in the length. Okay? So here's example 2. I think I'll go to a clean. First, let me. Let's see if they have this. I don't recall that they do. Let's just see. Nope, not yet. Oh yeah, wait, I'm sorry. I almost skipped over this. This is a graph, you might almost say a map of what's going on with Hooke's law. Hooke's law is good in this straight line portion because the more the delta L, that's a constant. Your applied force, the ratio of the applied force to delta L is a constant, so same slope. Okay? That's up to the elastic limit. What happens at the elastic limit? It doesn't go back to its original shape. There it gets deformed. Well, once it's deformed, you can stretch it and bend it, and it's not coming back. It's going to do whatever you tell it to do. Okay? So you continue stretching or stressing or whatever you want to. This is called the plastic region. Now it's not going back to its original shape. Wherever you leave it, it pretty much stays there. And you've seen a spring do that, right? You pull it too far, and then it stays there. Pull it further, it stays there. Try to compress it, it doesn't do anything. Okay? So that's the plastic region. Whatever you do to it, it maintains that. But if you keep increasing the length of it, applying more force to it, at some point you're actually going to fracture it. That's the fracture limit. Okay? So I guess we needed that before we didn't need it before we did the example, but they gave it to us. Okay. All right. I think we have to go back to our other slide. It takes a little while to do this, but it's not too bad. Okay. Yeah. Got bit by a mosquito or something, and it's just itching me like crazy. Okay. Here's what we got. A force of 5 newtons is applied to a spring whose elastic constant, which I call the spring constant, is 0.25 newtons per centimeter. Okay? So here we have the spring hanging down here, not doing much of anything, just hanging there. Okay? Now, we apply 5 newtons to it. Okay, that's the weight of 5 newtons to the spring. And the spring has an elastic constant K of 0.250 Newton per centimeter. Okay? Find the change in length. So what's our formula? This 5 Newton is our, what does Newton measure? Force. And the We are looking for the delta L. So how does force, K, and delta L relate to each other? What's our formula we just had? Anyone remember?
The whole, the delta force over.
Yeah, force over delta L is equal to K. And our force was 5.00 newtons. Now what is a newton, by the way? Give me its fundamental units. Newton is a kilogram meter per second squared. Oh, we've got a problem, Houston, don't we? We got this in centimeters. What does it need to be? In meters. So let's go take care of that first. 0.250 Newton per centimeter. Got to multiply that by something to get it into Newton per meter. Okay? Because that's what we measure things in, Newtons per meter. We measure it in meters. So, what unit do we need to put where? Always put the units in their place. What unit do we put where? Centimeters on top, is that what you said? And meters on the bottom, that's going to get it right. Okay. How many centimeters per meter or meters per centimeter? Second? How many cents in a dollar? 100. So 100 centimeters is 1 meter. So you move this decimal by 2 places, that's 25.0 newtons per meter. Now we can do it, I think. Okay? So that's over delta L. That's what we're looking for. And that's equal to 25.0 Newton. Oh! Why did I do that? Let's leave that in newtons. No reason to go to fundamental units. I thought there was. Okay. And 25.0 Newton per meter. Okay. We didn't have to change either, did we? Sorry about that, folks. Let's go back to what we had, and that was 0.25 Newton per centimeter. That's what we had to begin with. See, we can just cancel the newtons out, and now what do we have to do to get the delta L? I sure don't want it in the denominator, do you? Second? Actually, I would multiply by delta L. Okay? And then divide by 0.250 per centimeter. Okay? That's a weird unit. Okay, here the delta L's go out, and now we divide by 0.250 per centimeter. Okay? Now, move this decimal 2 places that way, that one 2 places this way. 25 will go into 500, well 25 will go into 50 twice, so that'll be 20 times. Okay? And you wind up with 20 centimeters. So it looks like the delta L equal 20 centimeters. What do we get? Yeah. Actually, I left off with 0, 20.0 centimeters, because we had 3 significant digits everywhere. So that's how far it stretched the spring. 20.0 centimeters. Okay. Does that make sense? Okay. And that's what they got to. All right. I don't think they're going to have example 3. In fact, I don't remember what the next thing they have. Yeah. It's the next page. So let's clear the ink. Can I clear this now? Okay. And let's do example 3. A force of 3 pounds, so F equals 3.00 pounds, stretches a spring 12 inches. That's your delta L is equal to 12.0 inches. What force is required to stretch the spring 15 inches? What force will stretch the spring 15.0 inches? Okay, that's what we're looking for. Now, same spring, right? We aren't changing springs on you. Same spring. So the constant will be the same both times, right? You could find the constant first and then go for it. Or, since it's the same constant, they don't ask for the constant. Now, I'm cheating a little bit here. But look at this. F over delta L is equal to the constant, which is also the same constant when, let's call initial, and this will be final. Okay? So this is initial, and this is F final over delta L final. So gets my drift of what we're doing here? That's got to be the same, unless you exceeded the elastic limit, which I don't think 3 more inches would do. So basically you have 3.00 pounds is to 12.0 inches as F sub F, final force, is to 15.0 inches. Now, I don't know if this is going to work. It seems like it should. Let's see if it does. I'm going to simplify this and make it 1 over 4. Okay? So that is going to be 4 times F sub F is equal to 15. That's cross multiply. Okay? And divide by 4. And you have your final force applied is 3.75. And that would be newtons. And that sort of makes sense. It's 3, I'm sorry, these are pounds, because those were inches. 3.75 pounds. 3 pounds stretched at 12 inches, 3.75 pounds will set at that. Let's see what they got. 3.75 pounds, good for them. Okay? Now, you could do it the way they did. Calculate your K, then multiply it by the nu, and that works. If you spend the time to do it. But since the K's got to be the same for both ratios, just set them each other and do a proportion. You see how that works? I mean, I'm just doing it a little bit easier way than the book did. Okay? All right. Ready for example 4? Count. Leave that a minute more? Okay. Now what the book did, they took the first ratio you knew, F sub I over that, calculate your K. And that's going to be 0.25, right? 3 divided by 12 is 0.25 pounds per inch. Okay? And then do F sub L over 15 is equal to, what did I just say, 0.25 pounds per square inch. So multiply top and bottom by 15, and you got it. Everybody got it? Okay. Let's do example 4. Can I erase? A support column is compressed 3.46 times 10 to the minus 4 meters. That's a pretty small amount. Under a weight of 6.42 times 10 to the 5th newtons. How much is the column compressed under a weight of 5.80 times 10 to the 6th newtons? So what is the compression under 5.80 times 10 to the 6th newtons? Okay? And guess what? The first bit of information there gives you the K. And it's the same bridge, same material, same everything. As long as you haven't exceeded the elastic limit, it should be the same K, right? So why do twice the work when you can do it all with one ratio? Okay? And that ratio would be force. I'm going to call it F1 over delta L1. That's equal to K. And that's also F2 over delta L2. Okay? Your F1 is 6.42 times 10 to the 5th Newton over 3.46 times 10 to the minus 4 meters as, skip the K, who needs it, as 5.80 times 10 to the 6th Newton is to the new delta L. Delta L2, whatever you want to call it. Okay, very much like we did before, we do a cross multiplication. Now, watch out with your scientific notation here. Let's call this delta L2, just to have a name for it. Okay, so that'll be 6.42 times 10 to the 5th Newton times delta L2 is equal to, multiply these two together, 5.80 times 10 to the 6th Newton times 3.46 times 10 to the minus 4 meter. Then just to get all the numbers in the right place, divide both sides by 6.42 times 10 to the 5th newtons. Okay, this goes away, that goes away, the newtons go away, and you're going to get an answer in meters, which is a good thing for your delta L2. And watch your exponents. In fact, if you sort of want to do away with the exponents, you can. You know, 10 to the 5th will go into 10 to the 6th 10 times, right? And 10 times 10 to the 4th will be 10, negative 4 would be 10 to the minus 3. Okay? So now you can just deal with your numbers. 5.8 times 3.46, divide that by 6.42. What does that give you? A little louder? 3.0? Oh, 12.0. Okay, I can't hear. Okay, 3.12. Oh, I just erased the wrong thing. Yuck. Sorry. I hope you still have your numbers down there. It was 3.12 times 10 to the minus 3, if I remember right, meters. Okay? So that makes sense. And if you want to do that, 10 to the minus 3 meters is 3.12 millimeters. Okay? That's a much smaller, a bigger number, smaller unit. That finished 12.2. Was it 12.2? Yeah. And 12.2 problems, you can do any of the odds 1 through, well, any of the odds 1 through 19. They have 13 uses a table there, so you can use the rest of them, use whatever it takes. And we'll begin next time with properties of liquids. Okay? Making good progress, I think. Thanks for hanging around the extra half hour. That gets us on the road a little bit earlier next Thursday. But good deal. Thanks so much.